Welcome to the cycle with many names. This is known as the tricarboxylic acid cycle, which is why you might hear it called the TCA cycle for short, also known as the citric acid cycle, also known as the Krebs cycle. Yes, all four of these names are completely interchangeable. You'll see at the bottom of the screen that says play the song. This song is very silly, but it was actually the first way that I was introduced to this pathway by the professor who taught me biochemistry, Dr. Vincent Cirillo, a couple years ago. So there is a study guide as part of the PowerPoint slide, so I would highly encourage you guys to go back and take a look at those. We had left off at one point talking glycolysis, and we had gone ahead and shown that you can go ahead and take pyruvate from glycolysis and go ahead and reduce it to lactate, which will then oxidize the NADH back to NAD+, so that NAD+ can go back into glycolysis. So we looked at that recycling of NADH and that ability of that pathway of fermentation to deal with your pyruvate and lactate under anaerobic conditions. But those are only for anaerobic conditions. So the grand question now is, well, what happens if you have oxygen? What's our other option? What you'll see here on this slide is that you've got part A, which is what we've spent some time already talking about. So doing glycolysis to pyruvate. And that's where we're going to be picking up the story, looking at how pyruvate can then be further oxidized to acetyl-CoA and then enter the citric acid cycle. So with that, your pyruvate is also going to go through a decarboxylation before it enters the citric acid cycle, and we're going to be spending our time looking at all the different steps in the citric acid cycle. You'll notice that we're also going to get more rounds of NADH out of here, as well as an FADH2, which is another reducing power. We'll also be producing GTP, so we'll also get some more energy out of it that way. You'll then notice that in part C, then that's all going to go to the electron transport chain, which will then be feeding electrons into that, which will then pump protons across a gradient into the inner membrane space of the mitochondria, which will then create a high amount of protons, which will then be able to go back down through an ATP synthase, which will produce ATP. And that's going to be our oxidative phosphorylation. So that last step is that oxidative phosphorylation. These pieces, the citric acid cycle, electron transport, and oxidative phosphorylation, is actually going to get us through the rest of the semester. Glycolysis and that citric acid cycle are oxidative pathways. They're going to produce reductive power in them, and that reductive power in the form of electrons, in the form of NADH, is going to be then fed into the electron transport chain, which is then going to give that yield of ATP. You're going to get around 30 ATPs per molecule of glucose. We'll be taking a look later as to how all that math works out. This is just a grand overview of the TCA cycle. And yes, I do apologize that I'm going to be switching back and forth between different names. To me, they're all the same, so it's like having one person with a whole bunch of nicknames. In my head, they're all the same. So as mentioned, pyruvate is going to be decarboxylated to acetyl-CoA. Acetyl-CoA will then enter the TCA cycle. In here, and we'll be talking about this more, you actually have places where different substrates in this pathway can actually go off to do other things. So some of these, while they are useful for just having that, producing that reductive power for the electron transport chain, some of these will also go off for other anabolic reactions. Each cycle then is going to produce 2 carbon dioxide, 3 NADH, 1 FADH2, and 1 ATP.